Hi, my name is Minji Kang, and this is my presentation for Physics Lab 2 projectile motion. The purpose of this lab is to compare the position of a projectile affected by gravitational drag forces, both experimentally and computationally. The object of the experiment was paper ball, and experimental model I use Tracker app, and for the computational model I use GlowScript. The main result of the lab was that the computational model with both gravitational and drag forces acting on the object was shown to align more with the experimental model. So there are five fundamental principles in the experiment. There's Newton's second law and position update formula used to find the updated position with the new terms, and velocity update formula used to find the updated velocity with the new terms. Drag force is has a negative b, which is the proportionality constant, and shows that it acts in the opposite direction of the velocity of the object. And gravitational force shows that it is directing towards the negative y direction with the negative mg. This is a lab procedure for the experiment. First, record a video of the paper ball being thrown up in the air in a projectile motion, then import the video into the Tracker app to measure the change in position of the paper ball at set time periods, then create a computational model of the thrown paper ball in a projectile motion in t seconds using GlowScript and input the data into the starter code. Plot the data from both experimental and computational models to compare the results of the experiment on a position versus time graph for both the y and x components. The system was the paper ball and surrounding was everything else, including gravity and air resistance. So this is the observational model. The paper ball is thrown in a projectile motion. Each red marking represents the different positions that the Tracker app tracks as the object moves. The graph on the right is a position versus time graph for both the x and y components. And in the observational model graphs, you can see that the x component is more linear compared to the y component graph. The total time was 0.333 seconds, and that was using the first two plots, we can find the initial position and initial velocity. And using the calculations that we found, we input the mass of the ball and the initial velocity and initial position of the ball. And then delta t was 1/30 because the camera catches 30 frames per second. And b is the proportionality constant. And then we changed the time to 0.33 seconds. And then this is the drag equation put into the code as well as the gravitational force and the net force by adding drag and gravitational force. And this was also the velocity and position updated formula. And these were the codes used for the arrows. Computational model, you can see that it is more linear and the y component graph is more parabolic. And now when the b changes to 0.01, it becomes a little bit more parabolic, even if it's not a big change. And data comparison, we can see that computational with gravity and drag forces are more similar to the experimental graphs. So deviations, there are external forces that could be acting on it that were not calculated during the experiment, position tracking errors, and calculation errors, such as rounding errors. Additional questions, do any of the models predict a terminal velocity? Neither of the models display terminal velocity because neither of the graphs show a horizontal line on velocity versus time graph. It could reach terminal velocity if the object was falling for longer, which would allow the object to reach maximum velocity from gravitational force, and the velocity would be constant, which means net force would equal 0. The paper ball thrown up in the air straight up would take more time to reach the ground because throwing the ball straight up maximizes the initial velocity. This allows the object to take longer to fall back to the ground, but because the object was thrown at an angle in our experiment, the initial velocity is split into both x and y components, which would limit the object from reaching a higher peak.